What if I told you that two of the most revolutionary and transformative technologies of our time could be combined into a singularly powerful idea? An idea that could reshape the very foundations of artificial intelligence as we know it. We're talking about the union of quantum computing, a realm where reality itself bends to the bizarre laws of quantum mechanics and neural networks, the workhorses driving today's AI renaissance. On today's episode of AI Talk, we'll dive into the audacious proposal of creating quantum neural networks. A concept so outlandish, so mind-bending, that it may very well represent the future apex of machine intelligence capabilities. So brace yourselves, listeners. We're about to take you on a journey that blurs the line between science and science fiction. A journey where the strange and nebulous world of quantum information meets the meticulously trained parameters of deep learning models. The implications are staggering and could one day give rise to an entirely new paradigm of cognitive computing. But is such an ambitious melding of quantum and neural even possible? That's what we'll try to unravel. Get ready to stretch the boundaries of your imagination as we explore the tantalizing intersection of qubits and neurons. To truly appreciate the potential of quantum neural networks, we must first understand the powerful capabilities that quantum computers bring to the table. At their core, quantum computers harness the mind-bending principles of quantum mechanics, like superposition and entanglement, to perform certain computations exponentially faster than classical computers. You see, instead of processing information as bits representing zeros and ones, quantum computers use quantum bits or qubits that can exist as zeros, ones, or mind-bogglingly, a superposition of both 0 and 1 at the same time. This quantum parallelism allows them to evaluate multiple possible solutions across parallel quantum realities simultaneously. It's like having an exponentially vast workforce of computational threads working in concert. But it gets even weirder. The quantum states in these parallel realities can exhibit a counterintuitive property called entanglement, where measuring or perturbing one state instantaneously affects the others, no matter how far apart they are. By ingeniously exploiting these bizarre quantum effects through specialized algorithms, quantum computers can achieve performance advantages that grow exponentially with the size of the problem. Tasks that would take our most powerful supercomputers billions of years can theoretically be solved in a matter of seconds. Of course, building a large-scale, fault-tolerant quantum computer is one of the most daunting technological challenges we face. But the potential rewards are simply too great to ignore, which brings us to the tantalizing prospect of quantum neural networks. Now that we've covered the quantum parallelism advantage, let's dive into one of the most ingenious and counterintuitive quantum algorithms, Grover's search algorithm. But first, a word of caution from none other than Richard Feynman, one of the pioneers of quantum theory. He famously quipped, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Indeed, trying to visualize the bizarre quantum realm is often futile and leads down a rabbit hole of flawed analogies. However, we're going to attempt just that with a rather unconventional example. Not because it's a perfect representation, but simply to catch a glimpse of just how strange this algorithm appears from our classical intuition. Imagine we have a case of 100 baby bottles, arranged in a 10 by 10 grid, each fitted with those familiar rubber nipples protruding outwards. All the bottles are filled with milk, except for one. Our goal: to find the bottle missing its milk content without having to remove and shake each one individually. Here's where Grover's algorithm seems to conjure outright sorcery. First, we set all the bottle nipples vibrating back and forth coherently. Then, through some mystical oracle process, we somehow cause the nipple of the empty bottle to start vibrating in the opposite direction, even though we have no way of identifying which bottle is empty. Next, we apply a peculiar diffusion operation akin to raking a comb over the vibrating nipples. This comb doesn't disturb the out-of-sync, oppositely vibrating nipple, but it does cause a subtle redistribution of vibrations among the rest. With each successive application of the oracle nudge and diffusion operation, the vibration amplitude of the empty bottle's nipple becomes amplified, almost as if some invisible force is progressively enhancing its out-of-sync oscillations. After repeating this ritualistic process just a number of times proportional to the square root of 100, one nipple's opposing vibrations become dramatic enough to easily discern the empty bottle's location. Like a quasi-mystical divining rod, Grover's routine has allowed us to pinpoint the missing milk, all without individually checking each bottle. It's a truth stranger than fiction, the amazing power of quantum computation. Now that we've witnessed the quantum magic of Grover's search algorithm, it's time to propose an idea that may seem equally outlandish, using this very algorithm to train neural networks themselves. You see, at their core, neural networks are just extremely high-dimensional function approximators. By adjusting the connections or weights between artificial neurons, they can model extremely complex data patterns. However, finding the optimal configuration of weights that yields the highest accuracy is a tedious process. It typically involves iteratively tuning the weights using gradient-based optimization techniques like backpropagation. This process can take thousands or even millions of iterations to converge, especially for large, deep neural architectures. But what if we could circumvent all those iterations using the quantum parallelism trick? Imagine that instead of iteratively optimizing, we could encode all possible configurations of neural weights into a superposition of quantum states. Then we simply run Grover's algorithm, with the oracle picking out the quantum state that corresponds to the globally optimal weight configuration. Much like it found the empty baby bottle, Grover's routine could potentially vibrate its way toward the ideal neural network parameters across the vast quantum parallel landscape. No more getting stuck in local optima. No more laborious epochs of backpropagation. We'd go straight to the solution in just a few quantum iterations, exploiting the exponential parallelism advantage. Outrageous? Perhaps. But this is exactly the tantalizing possibility that scientists are already starting to explore with nascent quantum neural network models. If realizable, this approach could completely upend how we go about training even the most sophisticated deep learning models. It could unlock a new era of ultra-efficient cognitive computing capabilities. The potential advantages of training neural networks through quantum parallelism and Grover's algorithm are simply staggering to contemplate. First, let's consider the sheer computational speedup. Conventional training schemes quickly become intractable for large neural architectures with millions or billions of parameters to optimize. Even on powerful GPUs and distributed systems, fully traversing the parameter landscape is a formidable challenge. A quantum approach could bypass this exponential bottleneck entirely. By encoding the entire solution space as a quantum state vector, we could effectively explore all possible weight configurations in superposition. Grover's routine would rapidly amplify and probe the globally optimal solution with just polynomially scaled quantum resources. But the quantum advantage goes beyond just speed. By directly mapping to the ideal solution manifold, we may be able to circumvent many of the pitfalls that plague classical training techniques. No more getting trapped in suboptimal local minima on the error surface. No more vanishing or exploding gradient issues. The global solution could effectively be pulled from the quantum landscape through constructive interference alone. Moreover, quantum effects like superposition and entanglement may innately favor more robust, noise-tolerant neural architectures, perhaps unlocking entirely new cognitive capabilities that classical models struggle with. Quantum neural networks could potentially reduce training times from years to weeks or even days. They may achieve higher generalization performance and accuracy benchmarks with less data hunger. And they could pave the way for next-generation AI applications that leverage quantum supremacy from the ground up. Of course, achieving this quantum neural revolution assumes we can build large-scale, fault-tolerant quantum hardware. But if and when that milestone is reached, the floodgates may open for an entirely new paradigm of cognitive computing prowess. And it all starts with an imaginative unification of Grover's algorithm and deep learning. As tantalizing as the prospects of quantum neural networks may sound, we must soberly address the formidable obstacles that stand in the way of realizing this ambitious unification. The first and most glaring challenge is the sheer scale of quantum hardware required. Even relatively modest neural architectures can have millions of parameters to encode into an exponentially large quantum state vector. Representing such high-dimensional spaces would demand quantum systems with an impractically vast number of qubits. Currently, state-of-the-art quantum computers max out at just a few dozen high-quality qubits that can maintain coherence. We are still orders of magnitude away from the qubit counts required to model neural networks of practical interest using a brute force approach. But the scaling woes don't end there. Implementing the all-important quantum oracle that picks out the optimal solution is another Herculean task. Translating the neural network's complex objective function into a sequence of quantumly controlled operations is a formidable programming and engineering challenge. And what about the lack of gradient information in this quantum approach? Neural networks crucially rely on error backpropagation and gradient descent to iteratively sculpt their weight manifolds. This path integral concept may be lost when directly mapping to quantum solution spaces. There are also more fundamental questions about noise and decoherence tolerance. Will quantum neural networks inherit the extreme fragility that plagues most quantum algorithms? Or could they potentially be more robust by leveraging quantum effects? While theoretical models have proposed ingenious hybrid quantum classical approaches to alleviate some of these issues, we have yet to experimentally demonstrate substantial quantum advantage for non-trivial neural network tasks. For the time being, the realization of quantum neural networks remains constrained to a thought-provoking "what if" in the minds of quantum scientists and AI pioneers alike. But the quest continues. While the grand vision of quantum neural networks remains squarely in the realm of ambition for now, it would be a disservice not to discuss the active research happening at the intersection of quantum computing and machine learning. From pioneering labs and academic institutions around the world, an encouraging picture is slowly taking shape. Theoretical frameworks are emerging for how to map neural network models onto quantum circuits and leverage quantum supremacy. On the experimental front, we are witnessing a steady progression of proof-of-concept demonstrations executed on small-scale quantum devices and simulations. In 2020, researchers from Russia demonstrated a rudimentary quantum neural network implementation using just 4 qubits to solve a simple classification task. While modest, it provided an early glimpse into quantum machine learning capabilities. That same year, scientists from Google's Quantum AI Lab showcased quantum computations of certain neural network functions and kernels on their 72-qubit bristlecone processor, an important stepping stone toward more complex neural network emulations. More recently, in 2022, teams from IBM and Xanadu published papers detailing quantum neural network algorithms and architectural approaches that could potentially achieve exponential speedups over classical models. However, substantive benchmarking remains elusive with today's noisy, limited quantum hardware. The general consensus is that realizing the long-promised quantum advantage for deep learning will require fault-tolerant quantum computers with thousands or millions of logically encoded qubits. Formidable quantum error correction schemes that can indefinitely preserve those delicate quantum states. Yet, with each passing year, quantum hardware capabilities grow more robust and scalable. Whether leveraging superconducting, trapped ion, or other exotic qubit modalities, the global race to build larger, more powerful quantum computers has never been more feverish. When that pivotal milestone is reached, quantum neural networks may very well become one of the first killer apps to showcase quantum supremacy solving practical, real-world problems. An epical moment that could catalyze a new epoch in artificial intelligence. The future looks bright and fundamentally uncertain. As we bring this mind-bending exploration of quantum neural networks to a close, one cannot help but feel a paradoxical mixture of optimism and uncertainty. On one hand, the theoretical promise of wedding quantum computing's exponential parallelism to the parameter landscapes of deep learning is unquestionably seductive. To bypass the computational bottlenecks, local optima traps, and extended training times that classical approaches face could mark an epoch-shifting milestone. Imagine building neural networks with superhuman reasoning abilities by directly mapping the entire solution space as a gigantic quantum state vector, to then vibrate into the optimal configuration like an intelligent Grover's oracle, surpassing what could ever be achieved through conventional backpropagation alone. Yet, we must remain tethered to the sobering challenges of scale that still separate us from this quantum utopia. Today's nascent noisy intermediate-scale quantum devices are still many years and engineering breakthroughs away from manifesting this grand cognitive unification. But if the laws of quantum mechanics have taught us anything, it is that reality reserves some of its most profound surprises at the boundaries of our intuition's domain. What presently seems outlandish may prove to merely be a failure of our classical imaginations. So as we stand at this uncertain crossroads, staring wide-eyed into the inscrutable quantum realm, we can rest assured that the intrepid pioneers of both quantum computing and artificial intelligence will continue pushing ever forward. For somewhere within that vast exponential state vector, an AI revolution potentially awaits. And on that inspirational note, we invite you to enjoy an original musical composition created by an AI system. One that poetically captures the wondrous yet nebulous qualities of quantum neural networks that we've explored today, a tantalizing interplay between uncertainty and possibility. Much like the quantum realms themselves, it evokes a feeling of being deliciously entangled.
Whispers in the night play, quantum shadows form the day, strings that bend and intertwine. where the future is now. Today let the rhythm of progress lead you somehow. Imagine the soundscape that pulses with innovation, a melody that defies all limitation. We're breaking barriers, we're pushing the line, exploring new frontiers.